In this lecture, I will review the solution for this system, a card which is subjected to a harmonic load. We use x as the coordinate to measure the motion of the card, and we use theta inside the card to measure the rolling of the disk. The question asks us to use Lagrange approach, and our goal here is to find the amplitude of the card and then finding out at what frequencies this amplitude becomes zero, at what frequency or frequencies it's become infinity, and then trying to draw a sketch of this amplitude for the card actually, and then try to comment on any interesting features related to this system. All right, but before we delve to the solution of this interesting problem, let's just review quickly some of the fundamentals that we learned in the past related to kinetic energy. If I have a particle, we learn that the kinetic energy for a particle simply T is half of m x dot, its velocity squared. It's independent of actually the shape because it's a particle. It means all the mass is being concentrated at one point. But when it's a rigid body like this disk, we learn that the kinetic energy is half of I theta dot squared. And this I, in fact, is with respect to its centroid, IG, which in this case is 0.0. I can just write it IO. The same disk now is rolling on the ground, and the instant center is point C. What we have here is that we know this rigid body, beside rolling, it also has a translational motion with velocity x dot, which these x and theta have that relation. Therefore, my kinetic energy consists of two parts. One is the rotational part, half of IO theta dot squared, and the second part is actually the translational kinetic energy. Of course, I can simplify that by substituting x dot with what we found here, which is r theta dot squared, relation between x and theta. If I factor theta dot, half of IO plus mr squared theta dot squared. Now, this relation is familiar for us because we know IO mr squared, according to moment of inertia, parallel access theorem, gives me IC. In other words, I can pretend that this disk for an instant is rolling at point C, and I can use that relation to find its kinetic energy. With the same concept, now, if I have a pendulum, a simple pendulum, when we say simple pendulum, it means we ignore the mass of the link. So no mass. It means I ended up with just a particle here, a concentrated mass. And my energy actually, if I find the velocity of that, which is perpendicular to the link, that velocity is L theta dot. Therefore, my energy, T, is half of m L theta dot squared. Keep in mind that here, Ig is 0 because it's a concentrated mass. All right. Or similarly, if I call this point O, I know that half of m L squared theta dot squared, if I rewrite that relation like that, mL squared, in fact, is IO, because I have a concentrated mass. Ig is 0, but IO is simply mL squared. Now, if I have let's say a pendulum, which we have to consider the mass of the link, like this scenario. So we'll use our standard formula. We say I have a rigid body. Its energy is half of Ig theta dot squared plus half of m Vg squared, velocity of center of mass. I can actually replace Vg, the velocity of point G, because we know if this is Vg, it simply is half of L theta dot. Therefore, it's going to be half of Ig theta dot squared plus half of m half of L theta dot squared. I can, of course, factor half of Ig plus m L2 squared theta dot squared, which similar to the disk scenario, now this Ig ml squared means IO, if we call that point O. And for a link like this one, if it's a slender bar, IO is, we know Ig is 1/12 ml squared. And if we use the parallel axis, IO gives us 1/3 ml squared. By parallel axis, I mean if you use that relation, substitute that, we'll get these values. All right. So far, you saw the relations are very easy and straightforward. Hopefully, now you know how to calculate actually this relation, right? So again, just to summarize, for a particle, half of m velocity squared. If a rigid body is being linked to the ground, it's simply half of IO theta dot squared. And we see the similar concept here for that link as well. But when you have a scenario where the disk is rolling, like the case here, we know that our energy consists of two parts, translational and rotational. However, when we simplify the problem, we realize that the instant center is a point that we can pretend the system is being joined to the ground at that point, at that instant. And lastly, for a system like that, again, using the same concept, we can write our relation as this. The scenario of kinetic energy becomes a little bit more complicated when we have each of those systems now being on a system that system moves as well. So for all of these systems, when I want to calculate the kinetic energy, first of all, I know I have a card with mass m. So that part is there. So I have mx dot squared. For this one, I have mx dot squared. And I have mx dot squared. But then we need to add the energy for the other component. Here is the disk. So if I follow the same concept that we explained for a disk, then I have to write it's half of m. Suppose the mass of the disk is lowercase m and its radius is r. Half of m, and then I, let's call its centroid G, Vg squared plus half of Ig theta dot squared. Be very careful. This is Ig and this is Vg, right? We do not write it with respect to point C because now point C is not on the ground. It's part of the card and it moves actually. Also, Vg, we need to be very careful. The velocity of point G, we know from the view of a person standing inside the cart, that velocity is r theta dot, right? However, for kinetic energy, we have to write it with absolute coordinate. It means that Vg now is r theta dot plus x dot. And Ig here, of course, for the disk is half of m r squared. All right, so here is our relation. Using the same concept here, I have half of m for this link, Vg squared plus half of Ig theta dot squared. All right. Ig for this link is 1 over 12 ml squared. What about Vg? Well, similarly, Vg, we can find its velocity, and of course it's perpendicular to the disk like that. However, since we are in vibration, we assume that theta is so small that I can pretend that this velocity is almost horizontal. Remember, this is just an approximation. It's not accurate, but that's an approximation which goes well when theta is small and we don't make our life complicated. So it is half of L theta dot. All right, so I'm just going to go back one slide. It's exactly that relation there that we have, half of L theta dot. All right. So it's half of L theta dot. But since I assume theta is small, my Vg now is then half of L theta dot plus x dot. Remember, the person standing outside watching the centroid, point G, that person noticed that the card is moving with x, the center of the pendulum is moving with half of L theta dot. Therefore, that's the velocity they see. So as you can see here, it's wrong actually to write the velocity of this link t for the link half of I-O. Let's call this 1.0 theta dot square. This is wrong. Be careful about that. Unlike the previous slide, which actually were allowed to write it as we did here, right? We managed to find out that the kinetic energy is half of I-O theta dot square. But keep in mind that in this scenario, your point O is being fixed to the ground. Fixed to ground. However, where we are on the card, this point O, of course, has its own velocity, and we have to write the relation like that, and you need to trust me on this. And continuing with the same scenario, half of mvg squared, and of course, if I write the Ig, our standard relation, theta dot squared, we know Ig is 0, because here I have just a concentrated mass, and point G, which is the centroid of that mass, it doesn't have any actually moment of inertia. What about Vg? Well, by now you should know the velocity of that point. We can approximate it to be simply L theta dot. Therefore, my velocity Vg here is L theta dot plus x dot. All right? Hope is clear now. And with this introduction, now let's start the solution for our interesting problem here. So the question asks first to derive the differential equation. Of course, that's the very first step using Lagrange equation. For Lagrange, I need to figure out the value for t. Actually, that's the most important part, and the kinetic energy. Now we know how to write it. I suggest you pause the video and write it, and then compare with my result. So that's the first part. I know it's half of mx dot squared. That's for the card. This is where you need to pause, write the rest, and then compare with my solution. Assume you did that. Now I'm gonna add then half of the mr squared theta dot squared, and I'm just gonna move that part a little bit here. And then half of m, the velocity of the disk, which is x dot plus r theta dot squared, right? The disk, its center is moving by r theta dot from the view of a person sitting inside the card. But for energy, we care about the view of a person is standing outside, and now they see that the center is moving by x dot, the velocity of the card, and point O. That's T, and I need U, the potential energy here in this scenario, only there is the spring, which is half of K r theta squared. So you may ask, what about that X? Well, this X is measuring how far this cart is moving to the right, right? And it has no effect actually on the spring. You can visualize it by simply thinking about, okay, if this cart moves for 2 meters to the right, still the stretch on the spring will be r theta dot, right? So if I manage to find T and U successfully, as you know from Lagrange approach, the rest are just some standard derivatives and nothing else. Let's get started. So the Lagrange formula, when we don't have any damping, simply is the derivative of T with the variable that we are interested, Q dot U with respect to Q equal to the load. So here I have for X, my Lagrange equation will be derivative of T with X dot, derivative of U with X equal to, I have a load in the direction of X, it's gonna be simply F sine omega T. If I do the derivative, which I'm just gonna skip the step and write you just the final answer, because I know it's easy and you should be able to easily do that. And we repeat the same process for theta. Remember, we are doing the derivative with respect to these particular variables, and you should be comfortable doing that. I assume it's easy for you. So I'm just going to write the final result, mx double dot, and then we have that relation plus k r theta equal to 0. Right. Here is our system of differential equation. We know it's convenient to write it in matrix format. Then we can do the operation on the matrices instead. So in matrix format, I'm going to have a 2 by 2 matrix. My vectors here are x double dot and theta double dot. And I see a lot of zeros here, which means my stiffness matrix is decoupled. And on the right side, I only have F and 0 here, and here sine omega t. Here is my differential equations or system of differential equation in matrix format. Now, since I have a harmonic load sine omega t here, to find the answer, we assume the response of xt is a constant. I'll show it with uppercase X sine omega t, and we assume that the response of theta will be, again, a constant sine omega t. It's convenient to do that in particularly for this problem, because this is a function that can gives us the answer. Obviously, I can find x double dot, which is minus x omega squared sine omega t, and theta double dot, which is minus theta omega squared sine omega t. If I substitute this into the matrix, do the math, simplify it, I ended up with an answer which is actually minus m omega squared mr omega squared and kr minus mr omega squared. I assume, and I told you before, this part actually is really boring because it's just some tedious math, and hopefully we don't make algebra mistake. So it doesn't need too much actually creativity. It's just for us being able to write this equation. So I suggest you pause the video, substitute this value, do the multiplication, simplify everything, and see if you get the same answer as me. And hopefully I haven't made any mistake and you get the same answer as me. If not, let me know. All right. Now, when we get to this part, we have a simple linear problem, which we can use the Kramer rules to find the response x, actually. So in the response x, you know what? I'm just going to write it down here. The response x is the determinant of the entire things here. Just going to be lazy and copy that one there. All right. Determinant of that part. So let's just put the determinant here. And for the numerator, actually, we just substitute the, sorry, let's just, I'm just going to find the right pen here. All right. For the numerator, we use the same actually determinant, except we put the first column, I just put f and 0 from the right side, and apparently it doesn't allow me to copy. Let's just write it, not being lazy, mr omega squared and kr minus 3 over 2 m r omega squared. All right. So it's interesting. It's okay. I have a hard time finding the right pen here. Okay, maybe we just use that. That's fine. All right. So what happened here? As you saw, simply the response of x according to Kramer is denominator, denominator is determinant of that part. And for the numerator, you substitute the first column with that, and you put everything here. All right. And you can do the same for theta. We just substitute the second column for theta with f and 0. However, the question is only interested in x. I'd better simplify that relation because it looks ugly and it's a little bit scary. So since it's just 2 by 2 matrix, it's going to be very easy to simplify it. Let me do that. Is equal to, I'm just going to write to you the simplified version. And hopefully I haven't made any calculation mistake. And you can compare with yours and tell me if I got it right or not. Omega squared bracket k m plus m minus 3/2, a little bit long, half of m squared omega squared, and I close the bracket here. Right? So that's the response of x, actually, that we managed to find in a simplified version. Now that I have x, I can answer the question that the problem asked me. At what frequency x is equal to 0? We set x equal to 0. It means f k minus m omega squared equal to 0. And it gives me omega equal to 2k 3m. Right? So at this frequency, x is 0. All right. At this frequency, x is 0. It does not move, which is interesting, right? At that particular number, something will happen to this system. No matter how large is this force F, how large is this force F, if these value K and M are in a way that our excitation, omega, like this one, is up to us, right? It's part of the system, how this force, with what frequency this force is being applied to the system. Then this card is not going to move, which is interesting, right? But this is how the math is telling us. Also, the question asks us at what frequency x become infinity, very, very large. And we know what to do. We set the denominator equal to 0. Again, I'm just going to be lazy and see if I can copy. So I set that value equal to 0. And it gives me omega equal to 0 and omega equal to, inside that bracket, 2k m plus m divided by 3mm plus m squared. Pay attention, the unit also is correct. For frequency, we have k over m, right? But if you think about the units, we have extra m in numerator, extra m denominator, so they cancel out, so the unit is correct. So at these two frequencies, x is infinity. And these two frequencies, or at these frequencies, x is infinity, right? If we, of course, this is the math, but if we pay careful attention, we notice something very interesting. That relation here is there, actually, all right? If you go back and look at the relation for finding the natural frequency, you recall, we calculate determinant of matrix K minus omega squared M equal to 0. And that matrix actually is that determinant. Right? You can try and you can test it. You have your matrix M. You have your matrix K. So you can write the relation determinant or simply determinant of K minus omega squared M equals 0. And this one gives you the natural frequency. Natural frequency. Which we're going to be surprised that that relation actually is the same as here. And we know at natural frequency, the amplitude of vibration becomes 0. So my first natural frequency is 0. Second natural frequency is that value, whatever it is. All right. And lastly, the question asks us to graph the response of this system. Let's just try to graph something nice. And we are done actually for the solution of this problem. We want to draw X, a graph of X as a function of omega, because we know it's a function of omega, right? Here is what we found, actually. We found that X is this function. All right, and we want to plot it. So we have some key values here to consider. We know that at omega equal to 0, like here, it becomes infinity. But because I have that negative actually sign there, all right, I have that negative sign there. I know that I'm going to write it down here for myself so I can write it better. At omega equal to 0, X is, let's just write down minus infinity. At omega equal to 2k 3m, X is 0. And again, at omega equal to that omega 2 that we found, X again is infinity, right? So then perhaps I better draw maybe a line here. Let me see if yeah, that's a good one. So maybe I'll draw a line here. And since the question doesn't ask us to do the exact number, well, let's just pretend that maybe this is (2k) over 3m. And let's pretend this is omega 2 at value. All right. So, and of course, this is omega 0. Therefore, my graph is going to be at infinity over here. And obviously, it needs to go to infinity up there. Remember, at omega 2 also, we are infinity. Since we start at negative here, infinity, it has to go up there. And then we'll start from a neighbor of that one. And again, it leads to 0. Why 0? Just look at the relation we have here. Since you have omega in denominator, if omega is very, very, very large, then we know that actually the value of the X becomes 0 because you're dividing by a very large number. All right. So here is the graph then that I got. And the question asks if we can comment on any interesting feature. Let's just focus on this omega. This omega actually is where x becomes 0. What does that mean? It means we have actually a vibration absorber at that particular frequency, right? So here I'm just going to add at this omega, the disk acts as a vibration absorber. So that's one interesting feature that we can observe, right? What does it mean? It means for the system that you have at that particular frequency, the card is not going to move, but the disk inside that is going to move and absorb all the energy. So it acts as absorber energy, actually. The second interesting feature is at omega equal to 0. So we have a system of 2 degrees of freedom, but its natural frequencies, one of them is actually 0. What does it mean? Natural frequency of 0 means rigid body. It means there is no harmonic motion. Let's go back to the system that we have. Remember, natural frequency means no external load. We're just considering the system without any external load, right? So if there is no external load in this system, what you have is a card that there is no constraint or resistance to return it back. It can continue with motion m and never comes back. So it means it has no frequency. It's just a rigid body. Of course, we added the external harmonic load. It means it goes back. It goes back and forth. All right. Hopefully it's clear and you have a good understanding of this system. And what else? I have a challenge here for you. Well, actually, this is the same system with a little bit difference. You have the same card, same harmonic force, or maybe perhaps I put cosine omega t here, doesn't matter. But this time you have a disk which actually is joined to the card at point O, all right? So information that we have, the distance between centroid and point O is given to you. The radius of the disk is R. Actually, I just selected the parameters like that one. But good to know. You don't need it for the solution of this problem that OG is actually 4R 3 pi. There is a relation then between R and R. The mass of the disk, or not the disk, actually the half disk is M. And suppose our IG is I, just use the letter I. So for this system, try to find out the value of T and try to find the value of U. Right? So your U here is going to be an mg delta H. And T, I'm going to leave it to you. You should be able to now write it down. You have your card here, which is half of mx dot squared. Plus, I'm going to leave the rest to you to see how you can complete it based on what you've learned in this lecture. All right. Thank you very much. I hope you enjoyed this lecture and see you next time.